And I was having computer issues this morning. I was going to look at other solutions, but we'll just focus on number 2 was a buffer solution. And so we'll look at buffers right now, and we'll spend some more time just talking about buffers. Buffers are mixtures of what?
Weak acid and weak base.
Yeah, and so it's just a weak acid, weak base mixture. But the situation is, when we have a weak acid and a weak base, they don't neutralize each other out to form some kind of salt and water. And so what we end up with is a stable mixture of acid and base. And what that does is it gives buffers unique properties. And so what are they? The most useful property of a buffer is that they have a stable pH. What I mean by stable pH is if you dilute it, normally when you dilute something, you change the pH, or you make it more concentrated, you change the pH. But if you add water to a buffer, the pH doesn't really change, unless you add a lot. If you add a huge amount of water, so that it becomes almost pure water, very little buffer components in there, then the pH will approach that. But they have a stable pH, and the reason they have a stable pH is, we can just show this by an example here. We have to make sure we have excess buffer. And so we have to have excess weak acid and excess weak base. So if I were to add, let's say, a drop of strong acid to this, so 1 drop of 6 molar HCl, what would happen? As long as I have excess buffer, then the acid here will be neutralized by the base. And that's going to completely consume the HCl. So I have no more HCl left. And what's going to remain is, some of the base will be converted into weak acid. And so what will happen here is this. The HCl goes to 0 molar. And then the weak acid and the weak base, the ratio changes slightly. That is, I lose a little bit of weak base and I gain a little bit of weak acid because when I react with weak base, it forms the conjugate acid. And so it didn't change much, just the ratio changed a little bit. Ratio changes. And the magnitude of the change depends on the capacity. Capacity is just a concentration of buffer components. So high capacity buffer means you have lots of weak acid and weak base present. A low capacity buffer just means the concentration of those is very small. You don't have much. And so if we add HCl to a high capacity buffer, it barely changes. We have a negligible change. That is, we get a minus X plus X type situation where X is negligible compared to the initial. If we have a low capacity buffer, then the minus X and plus X could be significant. Could be quite significant. In fact, if we have an extremely low capacity, we can completely wipe out the weak base. If we completely wipe out, let's say we had excess HCl. If we have excess HCl, then we're going to completely consume all our weak base, and then we're going to be left over with a strong acid, weak acid mixture. A strong acid, weak acid mixture is not a buffer, considered a buffer. And so this starts off as a buffer and it ends up as a buffer. Okay, as long as we maintain some concentration of bulk. So let's take a look at a specific example here. We're going to add 1 drop of HCl just to pure water, 6 molar HCl, to 250 milliliters of H2O. Okay, H2O liquid is not a buffer, and so let's see what happens when I do this. So what happens when I do this is I'm going to have a little bit more solution. 1 drop is 0.05 milliliters. 0.05 milliliters, and they're about 20 drops per milliliter. And so the total volume here is going to be 250.05. Did the volume change much?
No.
No, the volume barely changed. And so I'll have 250.05. This is kind of a negligible change. It's a negligible change for the water, but it would be a huge change for the HCl, because the HCl started at 0.05, now it ends up at 250.05. And so in other words, the HCl is no longer 6 molar. And so what we have to do is we have to do a solution dilution. And so I need to calculate the new molarity of the HCl after adding it to this. So I shrank this beaker here because it wasn't enough room. Actually, I think that's so the new molarity of the HCl, the solution dilution is the initial volume of HCl, 0.05, divided by the final volume of HCl, 250.05. So this is called a 0.05 to 250.05 dilution. And this is called the dilution factor. And I take my dilution factor and I multiply it by the original concentration of the HCl, which is 6 molar. And so when I do such a huge dilution like this, the molarity is no longer going to be 6, it's going to be a lot smaller. So let's plug in. It's a 0.05 divided by 250.05. So 0.05 to 250.05 dilution of 6 molar, which gives me a molarity of 0.001998. So this is 1998 molar here, HCl. And so what we tend to do is we take the 6 molar and diluted it significantly. And so it's now this. Well, HCl is a strong acid. You know? And so what we could do is we could do what we did in chapter 16. We could just do KA if I want to do all the steps. So we call this, in chapter 17, we call this step I, solution dilution. Step I, the initial step. And then in chapter 17, we go on to step 1. Step 1 would be taking the strongest acid plus the strongest base.
Wait, Professor,
Uh-huh.
for the new concentration of HCl, you divided what you added by the final volume? Oh, the total volume?
Yeah, the total volume.
And divided by the original
Right.
6 molar.
Yeah. Where this comes from is this equation here. Concentration final is equal to volume initial over volume final times concentration initial. And so in other words, C final times V final is equal to C initial times V initial. And then I'm solving for C final. And then I get this V initial over V final. This is called the dilution factor. And so all I do is like look at what was the initial volume of the HCl, 0.05. What's the final volume? 250.05, the total. And then times C initial, which is the 6 molar. So that's
Also, please, I would say
okay. Now, so what we're going to do we'll just take HCl is the strongest acid present. What's the strongest base present in this particular mixture?
That'd be the water.
It would be the water, yeah. So this is going to form hydronium and chloride. What's Ka for HCl? Ka for HCl is very large. In other words, strong acids dissociate or hydrolyze completely. So the initial here I'm going to have is 1998, wasn't it? And 1998 molar. Water, 0, 0. Change is going to be complete. So at the end of this, I'm going to have 0 molar here, 0.001998 molar here, and 0.001998 molar here. Now chloride, does chloride change the pH at all?
No.
No, chloride is neutral. So the only thing that's going to change the pH is hydronium. Now we got to ask ourselves, do we have to worry about Kw? You know, because this is an acid solution. In the acid solution, we got to find all the hydronium ion contributors. So HCl is one, and so we figured out how much hydronium we have in this acid solution. So can I stop here and calculate the pH, or do you think Kw might add a significant amount of hydronium to this? Therefore, we should do step 3, or actually, this is step 2. Step 2. So we did step I. Step 1. Step 2 would be Kw, because that's all that's left over that could contribute hydronium to this. We already did HCl. And so the question is, will hydronium concentration change much with the addition of the hydronium from Kw? In other words, should I go on to step 2 or just skip it? Just skip it. Right. I just skip it because what's the most hydronium I can add from Kw? You know, in pure water, it would be 10 to the minus 7, but with a common ion, it's going to be a lot smaller. So a lot smaller than 10 to the minus 7, is that going to make any impact on this? No. And so I'm going to stop here because based on the concentration of hydronium I have here, I don't think Kw is going to make any impact, and it's probably not worth the time to calculate because it would be negligible. The only reason I go on to Kw is if I were asked for the inventory. You know, then I do the Kw, but in this case, I'm not asked for the inventory. So we're going to stop here and calculate the pH. The pH is going to be the negative log of 0.001998. So I'll take the log of 0.001998 and pH 26994. So the pH changed significantly. I'm only allowed 1 big here, so we'll just say the pH went to 2.7. Now, what was the original pH of the water? The original pH of the water was, pH 7.00. So we went from a pH 7.00 to a pH of 2.7. That's more than 3 orders of magnitude difference. And so now the water is 1,000 times more acidic, more than 1,000 times more acidic. Do you see that? And so in other words, there is just 1 drop of HCl caused a huge change in the pH of the water. So much so that I wouldn't want to drink this. I mean, that pH is a little too low. 2.7, I'm not going to drink this water. Okay. Even though you think, the solution to pollution is dilution. Well, this wasn't diluted enough. I needed to dilute it more before I consider drinking this water. I'm going to drink a buffer, though. Well, maybe it depends on what the buffer is, but let's.
I got a pH of 2.92.
2.92?
Yeah. I think you forgot the 1 and you did the negative log.
Oh, is it 1998?
Yeah.
Okay, let me try that.
concentration was 0.001.
.001998. Okay, double check it again because I'm getting the same number. Did it come out okay?
Yeah.
Well, let's see what happens if I add a drop of HCl to a buffer mixture. So let's pick a simple buffer mixture. Let's pick a weak acid. Probably the easiest weak acid might be acetic acid. So let's take 250 milliliters of buffer. And this buffer, I'm just going to make it simple. So the molarity of the acetic acid, I'm going to abbreviate acetic acid as HAC. Okay, the abbreviation for acetic acid. And we'll just take 1 molar. Here. I'll just do 1 molar. Won't really keep track of C figs just yet. I'll just carry extra digits. And for acetate, for example, sodium acetate, I might pick. Sodium acetate is a strong electrolyte, and it's going to break up into sodium ions and acetate. Sodium ions don't do anything with spectators, so we're interested in the acetate. And so this is the weak acid, this is the weak base. The acid, this is the base. When the acid and base are conjugates to one another, then we call this a Henderson-Hasselbalch buffer or HH buffer. They're conjugates. Therefore, we have an HH buffer. If we have an HH buffer, then what we can do is we can use the Henderson-Hasselbalch equation. And so with an HH buffer, we can use the HH equation. We can only use the HH equation if it's an HH buffer. And that means the pH is equal to the pKa of the acid, HAC, plus the log of the base, which would be AC minus, over the acid, HAC concentration. Okay, so I'm going to need the pKa for the acetic acid. The pKa for the acetic acid is negative log of the Ka, which is going to equal the negative log of 1.8 times 10 to the minus 5, which is going to give us the pKa of 474. And then the acetate concentration I'm using is going to just be 1 molar. And the acetic acid is going to be 1 molar, so it's just 1/1. Molarity, we don't include the units. So, calculating the pH of what I have here, I'm going to have the pKa 474 plus the log of 1 to 1. The log of 1 is 0, and therefore the pH is equal to 4.74. And so this is the pH of my buffer mixture. The pH of my buffer mixture is 4.74. We have all kinds of buffers. We have buffers that are very acidic. We have buffers that are acid-base mixtures that have very low pH. They have a low pH because the acid is much stronger than its conjugate base. We have buffers that are close to 7, where the acid and the conjugate base have comparable strength. And then we have buffers that are much higher than pH 7 because the base component, the base is much stronger than the conjugate acid. And so it depends on the Ka. In this case, we know that the acid is stronger than the base here because the pH is less than 7. And so Kb is more dominant than Ka for this. So it produces more hydroxide than hydronium. Okay, next what we're going to do is we're going to add a drop. of acid to this. See how much the pH changes. So we'll add 1 drop of 6 molar HCl, and this is 0.05 milliliters, to 250 milliliters of this buffer. What that's going to result in is going to result in 250.05 milliliters. So we call this step I. Step I is solution dilution. In chapter 17, we have to do this quite a lot because what we're doing is we're mixing one solution, solution A, with solution B, and then we're going to have a combined volume. The combined volume is going to change the concentration. We need to weigh the concentration. Whereas in chapter 16, we didn't do a lot of mixing. And so this is the step I solution dilution, and we're going to calculate all the new concentrations. So the original concentration of HAC is 1 molar. And the original concentration of acetate, like, the acetate, again, we could just use sodium acetate and mix it with water. Get a concentration 1 molar. Here isn't going to be the new concentration. The new concentration of HCl, well, this is the same dilution factor. You see it's the same dilution factor? It's a 0.05 to 250.05 dilution. And so what that's going to result in is a 0.05 to 250.05 dilution of 6 molar, which is going to give us O 1998 molar. So it's the same. Okay, then we're going to calculate, although this wasn't diluted very much. When I look at the acetic acid was barely diluted. Look at the dilution factor for acetic acid. We're taking 250 initial and diluting it to 250.05. It's almost not worth it to do this calculation because it barely changed. It's just 1 drop of extra water. But we'll go ahead and calculate it at 1 molar. So what did this result here in? It's a 250 over 250.5 dilution of 1 molar. 250 divided by 250.05. And it barely changed, but it comes out to 0.9998 molar. So it was just slightly diluted. And what about the acetate? Do that too. The acetate was diluted by the same dilution factor. It was a 250 to 250.05. And it started off at the same initial concentration of 1 molar. These buffers are stable mix of acid and base. They're a stable mix of acid and base because, let me just backtrack just for a second, because they don't neutralize each other out. If I took acetic acid and tried to react with acetate, what forms? What forms is acetate and acetic acid. And so we're going to have a stable mix of acid and base, especially in a HH buffer. When they're unrelated, then we might see some kind of reaction with that. But this is going to come out the same, 0.9998 molar. We'll just leave it at that. Okay, that's step I. Step I is the solution dilution. After the solution dilution comes step 1. What is step 1? Step 1 is you take the strongest acid. So what's the strongest acid present? We have HCl, HAC, AC minus, and H2O. Out of all those, HCl would be the strongest. Then we have to take the strongest base. what would be the strongest base present? It's either H2O or acetate. And so we can check the chart there and see which one's stronger, H2O or acetate. So if we take a look, the strongest base would be amide here. And then let's go down until we find acetate. Here's acetate. They write acetate as CH3COO minus. And then we keep going, and then finally we're at water. Water is significantly weaker than acetate. Acetate's a much stronger base here compared to water. And so the reaction should be the HCl plus the acetate. What's this going to produce? Well, acid will be a proton donor. And so if HCl loses a proton, it's going to form chloride. And the base will be the proton acceptor. So if acetate gains a proton, it's going to form HAC. And so we'll have a proton transfer reaction here. Okay, then what we're going to do is we're going to carry all the concentrations from step I to step 1. And so the initial concentration of HCl here will be 0.001998 molar. Okay. The initial concentration of HCAC, or acetic acid, is 0.9998 molar. And the initial concentration of acetate from step I is going to be 0.9998 molar. This is our initial, and then our change, and then we have our equilibrium. Now, what is K for this reaction? When we look at this, it's not Ka, it's not Kb. What is the K for this reaction? And the K for this reaction, we have to know what it is. The way we know what the K for this reaction is by comparing it with Ka. So there are two things. We could use the rule of thumb. The rule of thumb is strong reacts to completion. What completion means whatever the limiting reagent is. Will react. Or we could look at it this way.
Professor? Okay, so I'm still lost. When I do the calculation for the concentration of HCl, I get 0.00119976. Not 0.001998.
Let me see how to
If
get
that's the case, then that changes the concentration. Or changes the pH.
Yeah, let me 250.05 times 6. Oh, 11998. Yeah. You know what? I forgot something. You're right. Thanks for thinking. This is going to be 0.00
That changes the previous problem.
1198. Yeah, I screwed it up. Did I forget to multiply by 6?
That's what I was lost the first time.
Oh, were you? Okay.
So when you take the negative of that, then the pH goes to 2.92.
Okay, 2.92. Okay.
The previous problem,
Yeah, so correct it on the previous problem. The previous problem, we should have this, which makes it 2.98, which still would be 1,000 times more acidic. Okay. So, yeah, sorry about that. It's my mistake. Okay, so I need to change this one here. to 11998 molar here. Okay, so we're good. So we have our strongest acid reacting with our strongest base present, but we need to know the K for this particular reaction. There's no chloride. Oh, there is chloride, but the chloride's tied up with HCl right now, so this starts up with 0 molar. Now, the K for this reaction we should know because we have a strong species, either strong acid or strong base. Whenever we have a strong acid or a strong base, it always reacts to completion, so K is large. Or we could understand it like this. If we have HCl plus water, we recognize that that's acid plus water, that's Ka. Ka for this is very large. Now, if we have HCl plus a weak base, well, if you look at the weak bases, all the weak bases are stronger than water. The only bases that are weaker than water are like nitrate, chloride. Is chloride even basic? No, we treat chloride as a neutral. So all the weak bases are stronger than water. You see that? There are some bases that are weaker than water, but those can be considered basic. So what that means is if we take HCl and an even stronger base than water, then that should be an even more favorable reaction. So K for this reaction we call very, very large to indicate that it's going to be even bigger than this. Now, if we take a strong acid like HCl and react it with a strong base like sodium hydroxide, then that's even more favorable. And so HCl plus a strong base, we're going to say the K of the reaction is going to be very, very, very large. And so this gives us like 3 levels qualitative K. So in this case, what is K going to be? Well, it's a strong acid plus a weak base, so I'm going to call it very, very large. Very, very large. Okay, then it reacts to completion, but completion just means whatever the limiting reagent is. But what is the limiting reagent in this case? Yeah, the limiting reagent is going to be HCl. So, well, we're going to completely react all of that. And so we end up with 0 molar. And this is going to be minus the same, plus the same, plus the same, because they're all 1:1 mole ratio. And so let's go ahead and do the calculation here. So I'm going to get 0.9998 minus 0.001199.8. This is going to give me 0.9986 molar. This is, the chloride is going to be 0.001199.8 molar. And the acetic acid will be 0.9998 plus 0.001199.8. So this is going to come out to 1.001 molar. Okay, this is step 1. After we're done with step 1, what we do is we analyze what's left over. So analyze remaining mixture. So when we analyze this remaining mixture, what do we have? We have no more strong acid, and chloride's a neutral, so we can kind of ignore chloride. It's not going to do anything for pH. But what we're going to have is we're going to have acetate and acetic acid mixture. An acetate and acetic acid is a weak base, weak acid mixture. A weak base, weak acid mixture is called a buffer. And if the acetate and the acetic acid are conjugates of one another, we call it a Henderson-Hasselbalch buffer, or HH buffer. And so in this case, when we analyze what's remaining, we have an HH buffer that remains. And so this is an HH buffer. The HH buffer is just acetate and acetic acid. So if that's the case, then step 2, we can use the Henderson-Hasselbalch equation. And that means we don't have to set up an isotable. We could if we wanted to. We could either do Ka or Kb. I would prefer the Ka. But step 2 is if we have a Henderson-Hasselbalch buffer, we'll use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is the pH is equal to pKa plus the log of the base to acid ratio. And the base to acid, these have to be both weak and they have to be both conjugates one another. Weak conjugates. So you can't use a strong acid or a strong base in the Henderson-Hasselbalch. And you can't use unrelated species. They have to be conjugates. So the pKa for acetic acid, the acid component, is 474. Plus the log of the base, which would be the acetate, over the acid, which would be the acetic acid concentration. And so we'll plug that in here. This is going to equal 474 plus the log of acetate is 0.9986, and the acetic acid is 1.001. Just having my calculator here. So this gives us a pH of 4.739. 4.739, did the pH change much? What was the original pH? The original pH was 4.74. The new pH is 4.739. And so what happened was, when we added the acid, we lost a little bit of the base. This is the minus X. And we gained a little bit of the acid. This is the plus X. And it depends on the initial capacity. The capacity is the concentration. The higher the capacity, the higher the concentration. And so let's say I added 1 drop of HCl. This is the change here. But let's say rather than having 0.9, what if I had 9.9? If I had 9.9 molar, then this 1 drop is going to have an even smaller impact on that. And so X is going to be smaller. And if this were 9.9 molar, then the plus X would be even smaller here. And so the higher the capacity, the smaller the change I expect here. And the change I expect from this is to, lose a little bit of base, gain a little bit of acid. That's what we saw here. However, if I go the opposite direction, what if I made this more dilute? If I made this lower capacity, then the change is going to be more significant. So if I made this 0.009, then I expect a very significant change. In fact, if I made this 0.09, it's okay. It's going to still buffer it, but the change in pH will be more significant. If I made this 0.009, then I've exceeded the capacity. And so let's look at exceeding the capacity of the buffer. The more concentrated it is, the more resistant it is to pH changes because the changes.
So you're saying the explanation for this is the change in pH wasn't significant after we added the 1 drop of HCl.
Right. The pH didn't really change. Yeah. Versus an unbuffered solution, the pH changed like 3 orders of magnitude. We went from 7 to about 3. And so the pH from 7 to 3 is 1,000 times, 10 to the third. This one, the pH barely changed. Let's look at a very low capacity buffer. Very low capacity. Let's say what I do is I dilute this. And so what I'll do is I'll take 1 part of buffer and add 999 parts of water. And so that would result in a 1 to 1,000 dilution. And so I'll take my buffer and dilute it 1,000-fold. If I do that, then the pH doesn't change. The pH still stays the same because I have the same ratio, unless I go overboard and dilute it much more. But I'm going to have pH 4.74, but the concentration of acetic acid, in this case, actually, do I want to do the solution dilution? Let me do this. I'm going to do the solution dilution here. This is free. Well, I'm going to skip a step here just to save time. And so I'm going to say that the acetic acid is 1,000 times more diluted. So what we're going to do is we're going to go 0.0099. Would that be 1,000 times more diluted? No. We need to go 000. We're going to go 0009998. And then we're going to do the acetate. The acetate is going to be 0.0009998 molar. Here. Okay, so originally this was pH 474. And then to this, we're going to add 1 drop of the HCl. This is going to be 250 milliliters. And the new HCl concentration will be the same dilution factor, 0.0011998 molar HCl. So this is going to be after step I. So prior to step I, it was 474 original. So then we move on to step 1. Step 1 is the strongest acid, HCl, plus the strongest base, acetate. And this is going to yield chloride plus acetic acid. And then the HCl, 0.0011998 molar. The acetate, 0.0009998. Chloride, 0 molar. Acetic acid, 0.0009998 molar. So in this case, what do I have as my limiting reagent? K is going to be the same, very, very large. The acetate is going to be the limiting reagent, so we're going to lose all the acetate. Since all these are 1 to 1 to 1, the minus and plus the same amount. And so let's go ahead and calculate what we have here. So this is going to be 0.0011998 minus 0.0009998. This is going to give us 0.00020. Molar. This is going to be 0 molar. This is going to be 0.0009998 molar. And that's going to be 0.0009998 times 2. Which will be 0.0019996. All right, so this is step 1. Okay, what do I do in the next step? In the next step, I analyze the mixture remaining. So how would I describe this mixture? Remaining mixture is strong acid, weak acid. In a strong acid, weak acid mixture, in other words, it's a matched acid mixture. In an acid mixture, we look for all the hydronium ion contributors. And so, remaining mixture is an acid mixture. In an acid mixture, we want to look for all the hydronium ion contributors. Here. And so what's going to be the biggest contributor of hydronium? Well, the biggest contributor of hydronium will be the strong acid. And we start with the largest K. Start with largest Ka. Because the base is, what's the strongest base present? Chloride or water? Water. And so I'll take the strongest acid, this will be step 2, and react with the strongest base, H2O liquid. It's going to form hydronium and chloride. Ka for this is very large. So it should react to completion. Strong acids react to completion. So this is going to be 0.00020 molar. Okay, that comes from step 1. Chloride will go down to step 1 too. And so the chloride will be 0.0009998. Hydronium ion will be 0. Even though this is a common ion, the common ion is going to have no impact on this because it's a strong acid. Strong acids are just one way. And so this is going to react to completion, which means I'm going to lose this. I'm going to gain, I'm going to lose 0.00020. I'm going to gain that same amount, gain the same amount here. And so at equilibrium, I'm going to have 0 molar HCl left. And the hydronium I'm going to have is 0.00020 molar. And the chloride will be 11.0011998. Chloride's not going to have any impact on the pH. So that's the hydronium we're going to get from the HCl. And then the next thing is we got to figure out how much hydronium we're going to get from the next strongest acid. What's the next strongest acid? Yeah, acetic acid. So we'll go on to step 3. Step 3 would be the next biggest K, which would be HAC plus H2O liquid. This is going to give us hydronium plus acetate. Ka we look up on a table. Ka for acetic acid is 1.8 times 10 to the minus 5. All right. When I have a strong acid mixture, then both acids contribute. Hydronium. We have to factor in both acids into the pH. But when I have a strong acid-weak acid mixture, then the strong acid dominates. The weak acid barely contributes. The weak acid barely contributes because of the common ion factor. And so what we're going to see here is I don't really need to do this step, but I'm going to just do it just to show this. And so what I'm going to do is these went to step 2. This went to step 2, but this acetic acid is going to go down to step 3 here. And so I'll take this acetic acid that we generated in step 1 and put it down here into step 3. And then the hydronium, I'm totaling it. So step 1 had none, step 2 had some, and so I'll start off with this much, 0.0020 molar. And then the acetate is going to come from step, acetate's 0. So we don't have any acetate left over from any of the other steps. And so we'll start at 0 here. So the change here is going to be minus x, and at equilibrium, we're going to have 0.001996 minus x, 0.00020 plus x, and then x. And so Ka is going to be 0.00020 plus x, times x, divided by 0.0019996 minus x. Okay, then we just use the simplifying assumption. 1, K is not that big, and 2, common ion. We have significant common ion there. And so hopefully it works. This will give us 0.0020 times x over 0.001996. Okay, calculate this. So I'm going to have 1.8 times 10 to the negative 5 times 0.001996 divided by 0.0002. And I get x equal to 0.0001796. Now, which will be the bigger percent change? The numerator or the denominator? The numerator. Yeah. So I want to calculate the larger percent change. So the percent change here is going to be the change, which is 0.0001796 over the initial. The initial is 0.0020 times 100%. It gives me 89.99% change. Did it work? No. So what we have to do is we have to use the quadratic instead. So the simplifying assumption failed, unfortunately, for this case. Let's go ahead and use the quadratic. We'll get it in quadratic form here. So I'm going to get x squared plus 0.00020x. So x squared plus 0.00020x. And then I'm going to multiply this 1.8 times 10 to the minus 5 minus x here. So that's going to be 1.8 times 10 to the minus 5. So this is going to equal minus 1.8 times 10 to the minus 5 x, and then I'm going to multiply these two together and see what I get. So I'm going to get 1.8 times 10 to the minus 5 times 0.0019996. And so this is going to be plus actually I'm going to write the scientific 3.5993 times 10 to the minus 8. Okay, so just combining all the terms, we'll get x squared plus 0.000218 x minus 3.5993 times 10 to the minus 8 is equal to 0. Okay, then I'm going to go to equation, quadratic, and then a is 1 equals, and then b is 0.000218, and c is going to be negative 3.5993 times 10 to the negative 8. And so I get an x equal to 0.000198. All right, so let's go ahead and calculate the concentrations. I'm going to do a double check here. So if I plug in the x here, let me go back to computational mode. I'll get 0.00199996 minus the x, which is 0.001098. And that gives me 0.001889.8 molar. And then we'll add this. This is 000, this 000. So this is going to equal 0.0003098. And then the acetate will just equal that, 0.0001098. So these are the molarities we calculate. Now let's calculate K for this and see if it works out. Yeah. And so I calculate K, it comes out to 1.8000 times 10 to the negative 5. So let's get. All right, so actually we had a strong acid, weak base mixture, but take a look. Was the weak base a significant contributor to hydronium in this case? In other words, the strong acid gave us 0.0002, and the weak acid gave us 0.0001. So we got 50% more hydronium. You see that? And so in this case, the weak acid was a significant contributor to this. And so in this example, it was important to do step 2. Now I have to ask, well, if that's the case, should we do step 3? What would step 3 be? KW. Do you think KW would be a significant contributor to hydronium? No, me too. I don't think so, because the most KW can contribute is to pure water, and that would be 10 to the minus 7, which would be 6 zeros. But it's going to be a lot less because of the common ion effect. Because the common ion effect is going to be like 10 to the minus 8, 10 to the minus 9, 10 to the minus 10. So if we add something like 10 to the minus 9 to this, that's 8 zeros, is that going to change the pH much? No, it wouldn't. And so based on the concentration of hydronium we end up with at step 3, I'm not going to go to step 4. We're going to skip step 4. The only reason that you do step 4 is if you need to calculate the inventory, right, of everything. And so here, we're going to stop here and then calculate the pH. So step 4 would be KW. And this should be insignificant addition to like 10 minus 4. In other words, 0.0003 molar. Should be insignificant contributor to that. Okay, so now let's go ahead and calculate the pH. We're going to stop here. Therefore, the pH is going to equal the negative log of the total hydronium. The total hydronium we calculated is 0.003098. Which gives us a pH of 3.5098, which gives us, we're only allowed, I don't know, 6 8 like that. Me too. So what happened to the pH? What was our original pH? 4.74. So our pH went from 4.74 to a pH of 3.51. Was that a significant change in pH?
Yes.
Yeah. And the reason we had a significant change in pH is because we exceeded the buffer capacity. You know, there was no buffer left to neutralize that excess HCl. And so we exceeded the buffer capacity. And so the higher the concentrations initial, the smaller the changes, the X, and therefore less significant. And so exceeded buffer capacity. Now, I want to talk about the optimum pH of a buffer. For acetic acid and acetate, the optimum pH is 474. The optimum pH is the pH when we have a 1-to-1 ratio base to acid. And so the example here would be the buffer system we just looked at. So let's say we have 1 molar to 1 molar. That is 1 molar acetic acid to 1 molar acetate. Then our base to acid ratio would be 1, or it could be 10 and 10, or it could be 0.1 and 0.1. The log of 1 is just 0, and so the pH is equal to pKa. And so the optimum pH is when we have a pH equal to the pKa. And the reason is because then we'll have equal capacities here.
Question. I'm just going back to the previous example. So we did step 3 because we have an acidic solution where both acids are contributing hydronium, right?
Right.
Okay. I just wanted to make sure.
Yeah. We're looking for all, you know, when we have a mixture of acids, then we look for all hydronium ion contributors. Cool. But sometimes we don't want, you know, how many people want a buffer that's pH 4.74? I mean, it's fine. But let's say I want a buffer that's not 4.74. Let's say I want a buffer of so let's say I wanted a buffer of with a pH of 5.00. Then if my desired pH is 5.00, then I want a buffer that has an acid with a pKa of 5.00. And so I need to look for an acid that has a pKa of 5.00, and then I go to the chart here and I look for it. And here's one, but this acid's too hard to work with because I would need both the acid and the base component. The base component I have to make myself, and so I don't see it here. There are none. Maybe the closest one would be the pKa is the power, so I'm looking at 5 here. The closest might be acetic acid acetate. Yeah. Okay, so maybe let's try the acetic acid and acetate. Acetic acid acetate is close. And so AKC acetate is close. The pKa for acetic acid is 474. And so what I need to do is I need to raise the pH a little bit. If I raise the pH, I just need to add a little bit extra base. And so this just needs a little extra base. This needs extra base to raise the pH. So we'll try it over here. How much extra base? Well, we can use a Henderson-Hasselbalch to calculate this. And so if I go, the pH is equal to the pKa plus the log of the base to acid ratio. And the desired pH is 5.00. And my pKa is 4.74. And the log of the ratio is the acetate to HAC ratio. Then what I'm going to do is I'm going to calculate the ratio of acetate to HAC. And so we'll subtract from both sides. So this is going to give me minus 0.26 is equal to the log of the base to acid. I'm not going to write it out. And then we'll take the anti-log of both sides. So that gives me the acetate, which is the base. Acetic acid, which is the acid, is going to be 10 to the minus 0.26. So what does that come out to here? .54954. Is that what you get? Oh, it's not. Sorry, it's positive 0.26. Yeah, you've got to subtract this from both sides. I was thinking of something else. So let me fix that here. And with the correct positive, it comes out to 1.8197. Is that what you guys get? Yes. Okay. So this is 1.8197 to 1. So I need 1.8197 parts of base to every 1 part of acid. Base to acid ratio. Okay. So what I can do is I can just go ahead and make this like this. If I put in 1.8197 molar acetate and 1.0 molar acetic acid, then what's the pH of this buffer? Well, the pH is just equal to pKa plus the log And in fact, I'm not going to make it this precise. I'll probably just do the log of, just make it 182 molar acetate. And so if I just made this solution as 182 over 1, what would that be? So take the log of 1.82, is that plus 474. Let me do that one more time. I get a pH of 5.0001. Okay, so I don't have to make it this precise. I can make it 182 over 1. We'll get the same pH essentially. See that? So this would be my pH 5 buffer here, and this should work. Now I look at the capacity. You know, it's going to have higher capacity in base because I have a higher concentration of base. So what that means is I can add more acid to this without overwhelming or exceeding the capacity of the base. The capacity of the acid is the same, but I can, as long as I maintain this ratio, I'm okay. And so I can change it. For example, if I invert this ratio here, like if I have 1.8197 and I invert it, then I could have I could have 1 part of base to every 0.54954 parts of acid, you know, or any equivalent ratio, or any equivalent ratio, as long as it's not too dilute. When you make the solution too dilute, then it approaches water. You know, you dilute it so much, it starts to become less and less solution and more and more just pure water. But to make a fair comparison, and to go back to what we were talking about earlier, I want a pH 7 buffer. And so let's go to this next example. And so I desire a pH 7.00 buffer. So let's go ahead and try to make it a pH 7 buffer. Okay, using acetic acid and acetate. All right, so the pH desired is 7.00. The pK is 4.74 plus the log of acetate to acetic acid. And then I'm going to try to skip some steps here. We'll just go straight to the acetate and acetic acid, which is going to be, okay, 7 minus 474 is what? 2.26. And then we'll take the anti-log of that. And so we'll get 10 to the 2.26. Okay. And this is going to give me 181.97. And so I need the base in 181.97 to 1 ratio. Base to acid ratio. And so, well, I just make the base 182 molar. Have you ever heard of a 182 molar solution? No. In fact, do you know, like pure acetic acid, what the molarity of pure acetic acid is? If I had a liter of acetic acid, let's figure out what it is. Well, let's figure out the molarity of pure sodium acetate. So I need 182 molar acetate. Can I get it? is it even theoretically possible to get 182 molar sodium acetate? So if I look at sodium acetate here, I look at the density. For every milliliter, it's 1.53 grams. And so if I had 1,000 milliliters or 1,000 cubic centimeters, it'd be 1,053. So 1,000 cubic centimeters would be 1,000 times that. So I would have 1,530 grams. So a liter of pure sodium acetate, which is solid, weighs 1,530 grams. Well, how many moles is that? Well, there's 82 grams per mole. So divided by 82.0343, that gives me 18.6 molar. So pure sodium acetate, as pure as you can get, is only 18.6 molar. That's pure. Can I get 182 moles in a liter? It's impossible. It's not going to fit in there, especially if I have to add water and acetic acid. What is pure acetic acid? Molarity. Pure acetic acid is also called glacial acetic acid. It's as pure as you can get. There's going to be a little bit of water because it takes on water. But it has a density of 1.05 grams per cubic centimeter, so times 1,000. And so that's going to be 1,050 grams in a liter. Divided by the molar mass here, divided by 60.052. That gives me a molarity of 17. 17 molar is pure acetic acid. And so we can't get these ridiculous concentrations because you can't shrink atoms. If you could shrink atoms smaller, then yeah, you could put more atoms into a liter, but we can't do that. And therefore, we're going to have to go smaller. So let's go ahead and go smaller. This is impossible here. So we can do 1.8. You know, if we do 1.8197 molar acetate, that's doable. But what would the acetic acid be? The acetic acid would be 0.001 molar acetic acid. In other words, 1 millimolar acetic acid. Does this have very much capacity here? No. Although we have plenty of capacity in acetate, we have too little capacity in acetic acid. Too little capacity. And that means this can be easily overwhelmed. This is lopsided. This is a lopsided capacity. So it's fine for added acid, but it would be awful for added base because just a little bit of added base will knock this out. 1 drop of sodium hydroxide and this is toast, this buffer. Do you see that? Pretty much? Okay. And so what that means is we don't want to go too lopsided. Now, we have the optimum pH. We also have the optimum range. Or just the range. And the optimum range is just trying to prevent things from being lopsided, too lopsided. And the optimum range is going to look at the base to acid ratio. We don't want this too lopsided, so we can go like say 1 to 10, you know, but we don't want to go 1 to 100. This is more 1 to 100. Do you see that? And that becomes too lopsided. So if we had a 1 to 10 ratio, then the pH is equal to the pKa plus the log of 1 to 10. So that's 10 to the minus 1. And so what we have here is the pH is equal to the pKa minus 1. And so this is going to be the pKa minus 1 here. That would be the pH. At the max, we don't want to exceed a 10 to 1 ratio. Sure. A 10 to 1 ratio, well, this would be the pH is equal to pKa plus the log of 10 to 1, which would be the log of 10, which would be plus 1. So this would be the pKa plus 1. And then, of course, the 1 to 1 ratio is just going to be the pKa, plus 0. So we try to keep it within this range and not exceed it. And so what this means is the optimum buffer range for acetic acid acetate is the pKa plus or minus 1. And so an example here would be acetic acid acetate is okay for preparing buffers between 3.74 to 5.74. So this would be the pKa, this has a pKa of 474. So it's not going to get too lopsided if we keep it, within a 1 to 10 or 10 to 1 ratio. And so that means we can go all the way down to 374 and all the way up to 574. So if I wanted a pH of 5 buffer, no problem. If I want a pH of 4.00, no problem. But if I want a pH of 7.00, then it becomes too lopsided. And so what I need to do is I need to find a buffer system with a pKa close to 7. And so if I want a pH 7 buffer, I need a pKa close to 7. And so let's take a look at something that's close to 7 here. This chart is kind of nice because this chart, they calculate the kBs for you. Most charts, they aren't so nice. They don't calculate the kBs for you. And so we're looking for something with a power of around 7. So we go, this is 3, 4, 5. We'll go weaker. Oh, here we go, 7. Oh, actually, there's one that's perfect. Look at this one, 1 times 10 to the negative 7. So this would be perfect because the optimum pH is actually the pH that we want. And this is going to form but there's one problem. And the one problem is actually more than one problem. More than one problem. H2S, problem number 1 is smells bad. It's really stinky. Do you know what it smells like, H2S? Rotten eggs. This is the rotten egg odor. That's problem 1. Problem 2, H2S is toxic. It's toxic at the part per billion level. And so we don't want to work. That's problem 2. Problem 3, H2S is gas. Working with gases is inconvenient. Problem 4 is H2S isn't very soluble in water. The max solubility of H2S in water at 25 degrees C is only 0.1 molar. So we can only fit 0.1 moles per liter in solution, so we can't have very high capacity for buffer. It's going to be low capacity. And so even though the pKa is perfect, the pKa would be 7 right on. This one's close though. 6.2, if we go to 10 times 10 to the minus 8, 10 times 10 to the minus 8 is 1 times 10 to the minus 7, so it's pretty close. Right? So this one's also close. 6.2 times 10 to the minus 8. Hypochlorous acid is close, 3.5 times 10 to the minus 8. And so these would be acceptable, even this one, except this is lead. We don't want to work with lead. Hypochlorous acid, I don't really want to work with that. Hydrogen sulfite. Sulfite is susceptible to oxidation to sulfate. This is probably better, the more stable. And so we'll pick dihydrogen phosphate. And so let's figure out what the pKa of dihydrogen phosphate is. And so if we desire a pH 7 buffer,
why wouldn't you go up to
carbonic acid? We could go up to carbonic acid. I mean, if we could drop this down to 1 times 10 to the minus 7, that's fine. But carbonic acid, there are 2 problems with carbonic acid. One, it's not stable. Carbonic acid decomposes into water and CO2. And problem number 2 is it's not very soluble. What happens is if you try to make a solution of carbonic acid, it's just going to bubble out CO2. And so what we end up with is just a little bit of carbonic acid and mostly CO2. And that brings up the problem working with gases and low solubility here. And so we could have gone up here. We could have gone up here too. This probably would do it. But working with aluminum is going to be difficult in this case because this is getting a little bit further. Actually, it's further away because 10 times 10 to the minus 6 is 1 times 10 to the minus 5. 5, there would be 2 orders of magnitude difference. And so carbonic acid, we could have picked that easily if it were easier to work with, but it's not. In theory, just as a hypothetical, yeah. Where we at?
Okay, yeah, we're out of time, so we'll look at making the pH 7 buffer next time.
Okay, let's stop here.